Hello, everyone. Hello. How are you? Good afternoon and good evening. Um, I'm looking at the friends. Thank you. Let's wait for everyone to come in. Okay. Yes. Good afternoon. Good afternoon. Well, then let's get started. Recording. Yes. It's okay. Well, we are starting another webinar. First, I would like to thank everyone for being here and for dedicating a little bit of their time to be here with us. Okay, my name is João Lemes, and I work in the export department at Editech Orthodontics. Nice to meet you all. Okay, now I have a errand. Okay, please don't forget to visit our official page, okay, Instagram at the Aditech Orthodontics, Facebook at the Aditech Orthodontics, and our website aditech.com.br. We are open to all questions, okay? We ask that you write them in the chat, please. And well, we at Tech will draw a gift for you to participate. You must stay until the end. Mr. Bruno will speak two words, and at the end when I give you okay, whenever writes the two words correctly, please. First and follow us on Instagram. Will be the winner. Okay. The gift is a new self passport. Okay. Uh, Now I will share with you your briefing presentation of our history. 1 second. 1 second, please. Okay. It's okay, Bruno. Um,
Okay,
Presentation.
I'm seeing you. Yeah.
Oh, okay. Thank you. Well, uh, yes. We are a Brazilian manufacturer of orthodontic and the 3D printing resina. Aretec Orthodontic was founded by Dr. Alexandre Lopes and the Dr. Gilza Lopes. And this year, we complete the 33 years of history. Currently, our CEO is Mr. Eduardo Lopes, son of Dr. Alexandre and Dr. Gilza. Okay. Today the company is recognized as one of the manufacturers of orthodontic products in the world. Okay. Okay. We export our products to all continents in the world. There are more than 90 customers. It is important to emphasize that our products comply with the strict international standards. We have a FDA, CE, and the ASO certificates. Okay. Yes, this is our product line. Here we have our complete line of products, brackets, tubes, archives, accessories, wires, orchid liners, static distalizer. Okay. Our our new launch. And if you want to know more about this product, contact me, please. Okay. We have different brands, different formats. Okay. This is a continual liner. We have elastic, auxiliaries. We have the bands here, aesthetic distalizer. Okay. And the other, our brand is Selfie for aligners and the virtual plan and our resin for 3D printing that we talk about today. This, oh, sorry. Here we have our complete line of resin. We have two brands, Aorus and Self Bioprint. Okay, Aorus and Self Bioprint. Porous aligner dental model castable is indicated for general use of prototyping and manufacture aligners. And our brand Selfie Blueprint is indicated for dental models, for example, bruxismal flakes and implant position. Okay. Next, yes, the brand itself. At Atec, we believe a lot in the future of orthodontics with the R aligners, correct? That's why we produce and we export our aligners, and we also have the self platform for virtual plan. Our platform is development by orthodontics for orthodontics. Therefore, Chinese company Angel Aligner, the second largest company in the world in the production of aligners and orthodontic technology. Both 51% percentage of Aritech last year. And now together we are going to be the largest company in the world in the production of aligners. So, yeah. Okay, see some photos of the company Angel Aligner. See photos of the team, our factor. Okay. Okay. Share. Yes. Okay, and now I would like to invite our specialist in resins for 3D printing, Mr. Bruno Oliveira. please.
Hello, guys. How are you?
Hello, Bruno. I'm fine, thank you. Thank you very much for accepting our invitation. Okay.
Okay. So, can I share my screen here?
No. Uh, yes, but the only the computer. Yes. Yes, it's
Okay.
okay.
So, hello, guys. My name is Bruno Oliveira. I would like just to introduce myself. I'm a technology manager from Astro Science, which is a company that is part of Agitex. We are the responsible for the 3D printing department here, and we produce we are the manufacturers of two brands, the Horus and Self Bioprint. Horus is the resins that we use for general use, and Self Bioprint we use for biocompatible resins. So the idea of this little chat today is just to clarify some myths and truths about 3D resins in dentistry. So I will give you some questions and answer that, and give you some explanation about some details of 3D printing. If anyone has any question, you just can put in the chat, and João will take a note, and at the end we can answer your questions. So I'm going to start talking about support, which is the main idea of this chat today. So w- the 3D printing supports have a real impact. Why do I need to use that? Why it exists? So to answer this question, and it's a truth. We really has real impact using supports, but to understand why it, and to understand how to use it, and the best way to use it, we need to understand first what is it, why are they needed, and impacts using or not using the support, and when to use it. So what is it? What is a support on 3D printing? So supports are some structures that we had to use uh, to 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 really support some parts on the some layers on the 3D printing process that are being printed on the air. So we have some uh, surfaces on some parts that are not flat. So we need to put some structure to support that on the printing. And we have a lot of ways to create this support. Some examples we can see here, and we have in this case is the crown part, and we can have this with splints. We can have that on models, common models. So we have different ways to use this support. Main the All of the 3D printing softwares today currently already use the automatic generator of support to make this process easier for the user, but it can maybe create some problems when we try to use just the automatic support, and we have to know when to trust on this support, and when to make some little adjustments. So why are they needed? If we To understand that, we need to know how the 3D printing works. So we have a part here, and the software will create layers from that part. So we make, when we set on the software that we want to print layers of 100 microns or 50 microns, we are defining this layer size. So with this height defined, the software will just slice the part, and we will have just all this slices here. So if we check this part and we check the layer 10, we can see that the layer is completely flat and over the layer before it. And in the layer 11, we have a little problem here because the slices, the part is already a little tall. So we are now introducing a new slice here, a new projection in this region here that is just starting on the air. So in this case, we will have a failure on the printing. If we check this a little bit on this by the side, we can see that that projection is completely over the air. So we need to support this part here. So what is the impact when I'm not using the support or when I'm not using it on the right way? So in this case, we are using support, but we don't put enough support on the part. So this part has a little height. It's this part is weighted than I thought. So my supports are not strong enough to support this part. So here in that case, the support will fail and it will broke. And when it breaks, we can see here that we have some lines on the part, on the tips. So in this case, these lines are caused by the lack of the support. The structure of the layers followed by the regions on over the support here will start to we start to become misaligned here. So that's why we have some lines visible here. Another example here, we can see it using too few support two, and then my models start to it will not be really have a good adhesion on the support, so it will uh, become displaced over the structures here and here, and this will cause a lot of failures here on the tips. In this case, and even here, we can see better how these crowns are. So here on the surface of the crowns, the layers are even uh, are not just misaligned here, but it's still laminated. In that case, in this last case, we have few supports to support these models. These are models for aligner, and these models just they fall to the tank of resin. So this is the impact of not using supports of the right way. So it can brings us to another question. It's is it possible to increase productivity by optimizing supports? And to understand that, we need to know when to use it and the impact of using these supports. Because yes, it's true, we can increase productivity, but we need to know the when to put the supports and the right way to do that. So using supports will bring an print time increase for our process. So when I need to put the support, my part need to be to have a higher height because I need a little space to put the support above the part. So because of that, my height of the printing will be higher, and then my printing time will increase. The consumption of resin will also be increased because I'm using resin, I'm using the material to construct this support, but these supports, there's no other use for me. They will be discarded after the printing. So I'm just putting some material away. And then because of these two features, I have a financial impact on at the end. I'm increasing my printing time. I can make less models at the end of the day, and I'm using a lot of more resin. So I have an impact, a financial impact here. So I need to know when to use it. And to show you that, I bring to you a little example here. If I have a model, this is a common model. This is the original one, and the volume of the original one is 10.8 milliliters. So if I use supports to create to construct this model, just like this situation here on the second on the middle, my volume will increase to 16.4 milliliters. And then my print time for this model with 100 microns of layer will be 44 minutes. If I think in a whole day of production, my consumption using 8 hours of production by day will be 1.44 liters of resin, and my amount of models that I will end at that day will be 88 models, because I will be able to print 11 rounds here using this model with this size. So if I adapt my model to not use support, and in that case, I will just cut this model in a way that this middle here will be supported on the platform, will be flat on the platform. And at the back of the model, I will create two holes. These holes are necessary to the amount of resin that will fill this part of the model will need to go through this region here. So in this case, if I'm not creating these holes, the liquid resin will be just uh, trapped here on that part of the model, and I will still waste resin on the process. So I need these two holes, or two or three, or anyway, at least two. And in that adapted model, my volume will decrease to 10.7 milliliters, just because I'm not using the supports. So it's 35% less volume than with supports. My print time will decrease to 36 minutes. It's an 18% less printing time than with supports. And because of that, my consumption by day will be 1.2 liters. But my daily amount of models will be 112 models, because I will be able to print 14 rounds at the same day. So we can see here, using less resin at the same day, using the same amount of hours, we'll be able to print more models. In that case, something about 30 models at least. So this is a huge difference, and it can have a huge impact here when we are thinking about production. So when to use supports, we can think that supports is just a bad guy, and we don't want to use that in any way. And that's not the case. We are just seeing that there's are situations that we can avoid it, but there are some situations that we have to use it. We don't have another option. In that case, in these situations used to happen when my models have irregular base. So it's not there's not another way to print a regular base without support. We just can do what I say at the last slide. When my model has a flat surface, I need at least one flat surface to be able to print the model without support. The other situation is to print crowns. Crowns has irregular base because it seems like it looks like a tooth a tooth at the surface. So we need the supports to do that. Surgical guides at the same situation and splints. So in that case, we have no option. We need to use support. But in the most case of models, aligners, models for aligners, models for common models for study or orthodontics models, we uh, the most part of the time we are able to print these models without support. The third question here is, it doesn't matter which resin or print you use. Uh, Nowadays, it's a myth, and I will explain better. We have actually impacts on the final models that came from the resin and then that came from printers. So it's not just the resin, it's not just the printer. We have a balance of two. So we need to know that. Some examples here: the resolution. The resolution in this first situation here, it has some impact of tourism, but we have a higher impact that came from the printer, and that happens because the resolution means the visual aspect of the resin, of the final part. And when I see the print layers, when I see the voxels, to explain better what the voxels are, we can imagine the surface of the model, and sometimes we look at the surface, we can see some horizontal lines or some irregular lines that came on the surface of the model, the printed model, and that surface are the voxels, are an effect caused by the process of the projection on the LCD and DLP 3D printers. So when my resolution of my machine are higher, when my voxels are uh, reduced, and then I'm not able to see too many voxels, and my surface seems to be more uh, more plain. So it's better to there is a visual effect, a better visual effect. There has been impact on that too, but it's not so significantly because nowadays the most of the resin has a higher resolution that are able to see that effect. The print speed is a parameter that are impacted by both resin and printer. So it impacts directly on my productivity, but the resin are essential in that situation, because if I have, for example, a resin with 10 seconds of curing layer, 15 seconds of curing layer, we will probably spend a lot of time printing that resin. But the machine are also important as the resin, as important as the resin, because when I have the printing speeds of the machine, the motor speeds of the machine too low because of the construction, the mechanical construction of the machine, or even the electronics. Um, we are also spending time to make the movement between layers. When the layer projected, the motor goes up and then goes down again, and this process are repeatedly by over all the layers of during the printing process. So if I have a resin with 2 seconds of layers, but my machine is too slow, my printing time will be higher. And if I have a resin with 20 seconds uh, of layer curing layer, and my machine are very fast, I will still have a higher impact, a higher time printing. So I need to balance these two situations. I need a fast resin, but I need to a fast machine. Then the next situation is the flexor strength. Flexor strength here is a parameter that are essentially called parameter, a feature of the material. So it's all about resin. But we are here thinking about the resin calibrated for the machine, because in the case that the resin and the machine are not calibrated, we can actually have flexor strength problems. Will create fragile models, but will not be because the resin, but actually because the calibration process. We will talk about that later. Waste. The waste is actually a parameter that is caused by resin too, because we are talking here about viscosity. Higher viscosity will cause some difficult of the liquid to flow, and we can imagine that thinking about yogurt and water. If I have a cup of water and then I just turn this water off the cup, we will see that there's almost no residue on the cup, and if just a little drops. And if I get a cup of yogurt and I do the same, just drop the yogurt out of the cup, we'll see that a lot of yogurt will stay at the surface, the internal surface of the cup, because the high viscosity of the yogurt. So the same happens when I think about the resins in 3D printing. The parts are immersed on the liquid, on the resin, and then when that part will be removed of the liquid, that liquid will still stay trapped on the part because the high viscosity. So when my resin has high viscosity, I will waste more resin. So it's interesting when when I'm able to have resins with lower viscosity. There's just a point here, because it doesn't mean that every resin with higher viscosity is bad, because sometimes we need that some characteristics of the material that are created because of that viscosity. And for example, ceramic materials, just like crowns, resins for crowns, this kind of material needs an additional material that are the ceramic, and it causes the effect of the high viscosity on the resin. So I need that material to increase my flexor strength. So I can't avoid to use that high viscosity. So in this kind of situation, it's something that I had to deal with. Uh, Usability to use, this to the user. This is mainly about the printer, because when I have good printers, expensive ones in general, we need less user intervention. Sometimes some machines are actually automatic, or try to make the process more automatic possible as possible. So this is completely responsibility of the printer and the software. Supports failure. In that case, we have some problems caused by resin, and most of the time by the resin, and sometimes by the printer. The the the, the resin, some characteristics of the resin can make the supports fragile. Some features can make the supports more flexible, which makes a necessity of uh, supports that are more that has a higher diameter. So we need to understand our material to use the correct support on that. And the printer, impact too, because sometimes if we have some printer that has a higher speed printing, higher motor speed, we can make the support fail. It can crack during the process of the movement of the motor. So both of them has impact on the support's failure. And all of that shows us that the main thing here, it's not necessarily the printer or the resin. So we have a very important paper here that is uh, that is made by the technicians on the laboratory, because he's the responsible to set the correct parameters, to calibrate the resin, to make to check if the Teflon is correctly installed, is not already it doesn't need to be changed. So we have a huge impact here on the technician of the lab. It will be the main paper for this. The first question here is a different resin. Oh yeah,
Mr. Bruno, excuse me. Don't
no
forget.
problem.
Thank you.
Yeah, I almost forgot our first word of of our, that you need to take note here will be printer.
Yes, printer. Okay. Thank you.
No problem. So here we are talking about LCD and DLP printers. There's really differences. I really need a different resin for each type of printer, for LCD and DLP printer. So now, currently, it's a myth. We already had that problem on the past when we used to have common LCD machines, but now we have some LCDs with the monochromatic structure. These new LCDs were created just to have a better effect when the LCD is exposed to the UV, because the UV are really uh, damaged to the LCDs, the normal LCDs, and these monochromatic are more resistant to that, and it makes it turned possible to the manufacturers to increase the power of those machines and to make those printers faster. And because of that, we now can use the same resin for DLP and LCD monochromatic printers, or most of the time, almost the same parameters. So here I bring to you some examples of features of each one of them. We have the projection, the resolution of the projector or the LCD. In that case, the DLP machines used to have up to 2K of the resolution. So we can imagine the full HD is the resolution that we are used to see on good TVs on the past, and now we see 2K, 4K, 8K, and so on. And for DLP, we used to have up to 2K. It doesn't mean that doesn't exist any DLP with 4K or more than that. The problem here is the cost. The cost of these DLPs are very expensive. So that's why usually we don't see more than this, more than 2K on DLP machines. So, and the LCD has a lower cost in that case. So we can improve that. And here we can see nowadays the LCDs with up to 8K, and there's an announcement of Anycubic, a recent one, that are announced a new machine with 2K of resolution of the LCD. So we are improving that a lot. but that has an impact of the printer resolution. Actually, here now we are talking about the resolution, the fewer the smallest detail that the printer can print. So on DLPs, we can go to uh, down to 50 microns, our smallest detail, and for these LCDs, down to 28 micrometers. The build size of two nowadays is actually the same. We have printers with 190 by 120, and it's a common huge size, but we already have bigger than that. We are here talking about common printers, but we know that we actually have some special printers that has very large build size, but that's not the case here. Print speed, we can see on DLPs that we can go up to 30 millimeters by hour, and on the LCDs we already checked some printers that go to up 50 millimeters by hours. But this is about the speed that the printer are able to reproduce on the motors, but it doesn't mean that you can print at that speed. You need a correct resin for that, and we need to have this careful. The cost of DLP are very higher than the LCD ones. So that's because of the main structure. The DLP are expensive than the LCD panel. Easy to use, again, the usability. DLPs used to be easier than the LCDs to be used because of this high cost of the machine at the end. The manufacturers are able to create some better structure regarding to software, to Wi-Fi connection with the printer, that we can just send the printer directly to from the computer. We don't need to use a pen drive. We can make this process easier, which we cannot see on the LCDs at most. And another situation here is because of the the way to calibrate, the way to leveling the machine. Usually the DLPs are easier to make this leveling, are not so common, are not necessary to be to have this leveling remade. So we have some situations that it's better to it's easier to use in DLP. And here I want to make a link with parts replacement, because on the LPs we almost don't need to replace parts. The DLP has a high time of life, so we can think here on machines that you will use 50K hours of printing. So differently of the LCD ones, we need to replace the panel. We need to replace frequently. Even with the monochromatic ones, we reduce the time, but we need to replace it. So it's make that makes the usability and the replacement of the parts worse for the LCD ones. And then we have quality here. The quality, the final aspect, the final visual of the part is almost the same nowadays for both of the technologies. So what is the consequence of this choice of the equipment when I think about the LCD and the DLP? And to answer that, I want to bring you an example to show that it doesn't matter exactly necessarily the LCD or the DLP technology, but what really matters is what I want to do. We need to bear in mind what I want to do and what is my expected result. So at the left side here, we can see that we have a printing made by DLP technology. Both of them were made on castable resins to the castable process. And here we have an XY of the machine resolution of 100 microns and a Z with 100 microns too. It's not using antialiasing. Antialiasing, it's a software resource that makes easier than for the software to smooth the surface of the models to avoid the voxels. So in that case, we are not using in both of them just to show the example. And this machine costs, because it's a DLP1, 500 to $5,200. In this case here, we have one with LCD technology, the XY resolution 47 microns, and you have the Z with 50 microns. So here we have a cost of $600. So we can see that the cheaper machine brings me the best result that I want, and the expensive one that doesn't couldn't bring to me. So why is that? Why that happens? And that happens because my parameters here are incorrect for my application. And it's not about the cost, it's about the parameters of the machine and the parameters of the printer, the printing process. So an example that I used to use here is I can buy a Ferrari. I will spend more than 1 million here, and then I can try to use that to pull a truck, and it doesn't work because the Ferrari wasn't made by that. But if I use a tractor for the same thing, I will spend a much less money, but I will achieve my goal. So we need to be careful with this. Well, the question 5 is: can temperature change affect my quality, the quality of my printings? And the answer is yes. It can have a high impact here. And the main reason for that is about the viscosity change. When my temperature goes down or goes higher, my viscosity, the viscosity of the resin will change. Higher temperatures used to increase to make the resin more fluid, and lower temperatures can use to increase the viscosity and makes it harder to flow. So this situation causes an influence on the resin return speed. And what is that? When my printing process are happening, the motor used to the projector just cure that layer. The motor goes up, and then this layer cured are that resin on the layer cured are just removed. So the amount of resin at the sides needs to flow to the center again. So this is that resin return speed. If my viscosity is too high, the resin has some difficulty to flow to the center again. And if that happens, I need to wait more time by the motor to project the second layer. And if I don't do that, I will my layer will become without resin. So I need to pay attention on that. And actually, it causes some calibration change too, because the curing time will can be decreased or increased depending on the situation. My higher temperatures used to accelerate some curing process. So when my temperature goes down, usually my cure time will be increased, may be increased. Here we are going to talk about SLA laser for dentistry. So this SLA laser is not for dentistry. Sometimes we see that question. And actually, it's a myth. Yes, it is too. But we have some advantages here. We have some benefits, and we have some disadvantages too. So I just will show you the both cases. The benefits of the SLA laser is the surface aspect of the part, the final part, will be smooth because the laser process use a dot with just like this red one I'm showing here, and then when the layer are being cured, this dot will creating the curves of the layer. So organic models, just like tubes and they use in dentistry, are has a better effect, smooth effect when I use this dot to create the surfaces. Different of the DLP that use pixels, just like I said, just like a TV on this TVs. We use pixels, and those pixels will create the surface using this rectangular pattern. So because of this rectangular pattern, I will just have this voxel effect. That's I just like I said on the last slides. So this is the effect of the DLP on organic models. That's why SLA laser has a better surface aspect. But we also have some drawbacks here, and it's mainly because about productivity. If we see here, the laser SLA needs to cover all the layer before go to the next one, and the DLP just project all that layer at the same moment. DLP or LCD in that case, we can see down here. So the same time here where the projections go to 40, here we are going to the first one. And this becomes worse when we think in productivity, because if I have one model on laser SLA and we spend X time, and if you have 10 models, we will spend 10 times more. So the number of models has a high influence on the printing time, different of the DLP or LCD that use the same projection for one or for 10 models. So it doesn't matter if I'm printing one or printing 10, my printing time will be the same. We is better for productivity, and we can see that looking here on the models by day, using SLA, we can go up to 64, and using DLP, we can go up to 120, depending on the machine. And the printing speed here on SLA will be something about 16 millimeters by hour, and for DLP, 50 millimeters by hour. The other question is the use of PPE really necessary? So we actually need some protection equipment. Yes, we really need that, and the why of that is because we are sensitive. We have some sensibilities to the reagents of the resin. So this sensibility is different from one user to another. So we cannot expect we cannot wait to have some allergy or some problem caused by this contact. We need to use PPE. And the alcohol used to clean the resin is also has also effect on our skin. So we need to take care of it too. And another doubt. Well, but if I use biocompatible resin, I don't need to use gloves, because the resin is biocompatible and it will not have any reaction with my skin. Biocompatibility is a feature of the final part, which means that I really need to use the same PPE that I used for the other resins. It doesn't mean that because my resin is my resin solid, my part solid, my final part solid is biocompatible. It doesn't mean that the liquid resin is also. It's necessary to calibrate my printer and my resin, and why? And yes, this is true too, because every resin is and every printer is requires calibration for the first time at the first moment of use. And it happens because for the resin, we need to adjust some energetic needs of the resin, of the material. We need to adjust from a machine to another, and between machines, even if it's the same model of machine, because we need to compensate some constructive aspects of the printer. So we need to take care of it, and we need to compensate expansion and compression of the resin. It can be also a feature of the material. When we undercure the resin, uh, which means that I'm not offering for the resin this the enough energy that it needs to be cured, to be correctly cured, we have some problems. That is, support detachment will be cause a completely failure or partial failures here. We have also layer detachment, because sometimes my part is completely flat to the surface, but my layer is detached. So I have a problem in that case too, because of undercure. And we can have also a loss of details here. We can have, if we see here the calibrated model, we can see that we can read Astro 3D 2019 here perfectly. But if we look under cured model here at the site, the holes are more open, so we lost some detail here, and the structures are lower than the real. So that happens because I don't have enough curing time on the printer. It has also a high impact here on the strength of the material. Here is the calibrated model, and here is the same, but without the correct calibration. So we can see here that we have almost 50% of the loss on the loss of the strength. Here, on the other side, you have actually the overcure effect. And the overcure happens when I offer too much curing time for too much energy to the resin to cure. So on the overcure, we have the holes closed than it should be, and the structures are bigger than the real. So in that case, we cannot see enough details. So we are actually losing dimensional. We are losing precision on the material. The other aspect here for calibration is dimensional costs. So dimensional, we are talking in the last slide about the resins effects on the calibration, and now we are talking about the machine calibration. So the machines, even are when they are the same model, they are made by a manufacturing process. So they are different from the projected when we are executing that assemble. So these differences are compensated by the calibration process. And Another factor here is the compression and expansion of the resin. So in both cases, we have different dimensional aspects here that we expect to have. So we used to adjust the scale factor to compensate that effect. 1 second. My project, my slide is a little uh, slowly. Okay. So, and what is the real effect of this dimensional discrepancies? So the models doesn't fit the real. When we has a model that is calibrated, we can see that the aligner in this case is completely adjusted to the model. But when the model is not calibrated, the aligner doesn't fit the right way. So if we try to do this, for example, in this case, we print this model for aligners, we thermoforming this aligner, and then we send to the customer. When it tries to use the aligner, it won't fit to the tooth, to the arc. So that is the problem to dimensional not adjusted. I'm sorry by these delays.
No problem, no problem.
Okay. So another common question is, can I use any resin for any application? The applications are exchangeable, and it's a myth. No, you can't use that. Some applications have your particularities. So we have some examples here. For example, splints, surgical guides, crowns, aligners. Each one of that has your material needs. Splints needs to be translucent, needs to have strength, but needs to be biocompatible. Surgical guides also needs to be biocompatible, high strength, but there's need to have a high dimensional accuracy. And crowds, we need a higher strength, so sometimes we need some ceramic material, and we have to cover some other situations here to can really use that for crowns. And aligners need to have high strength to thermoforming, but doesn't need to be, at least here in Brazil, it doesn't need to be biocompatible because it's not going directly to the mouth of the patient. It just need to use to be to mold to thermoforming the aligner. And just like I said, the splints, for example, the applications for that is for retainers or the splints itself, knife guards, stabilization of orthodontic and restorative works. So in that case, we need translucent and high strength. But if we're thinking on surgical guides, we need that for surgical guides for implants or gutters for orthodontic surgery. So in that case, we need high dimensional accuracy, stability, high strength, and are different parameters for each resin. So we need to respect these needs. And here I'm gonna bring to
Excuse me,
you a little.
Mr. Bruno.
Oh
Excuse me.
yeah,
Please don't forget our second. Uh,
exactly. We have here
yes,
our second word,
second
and our
word,
second word
art,
will be splint.
link.
So yeah, we have splint now.
Yes, thank you.
So for our last question, how to evaluate resin? So I'm gonna bring to you some parameters to watch when choose the right resin for my application. And what we need to see is first print quality, resolution. Resolution is it's necessary, but we need to be careful what we think what is resolution. Sometimes we think that smooth models are the ones with the better resolution, and it doesn't true because what the high resolution of the resin is when the resin are really reproducing what is being projected by the machine. And when the machine is projecting some, for example, in DLP or LCD printers, the machine is projecting square, square flat planes, square projections. So my pixels are being visible on the projection. So my resin needs to show that, even if it's not what I want. So sometimes you see some resins that are completely smoothed by the surface, and if it's you controlled by the software, it's not a problem. Actually, it's a plus. But if it's an aspect of the resin, it's not a good thing because when it comes from the resin, actually it means that the resin are not really constructing what I'm sending to it. So resolution means to the resin really show exactly what I'm projecting to it. Print speed, I really need to have print speed, but remembering about the slide when I talk about speed and print speed of the resin and the machine. So we need to balance both. It doesn't. It's not enough just to have a high uh, 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 resin with high print speed, but a slow machine. Flexor strength. We need to see if the resin has flexor strength enough from application. It doesn't mean that all resins need to have high strength. Sometimes, for example, some resins that has an aspect of some flexibility, it doesn't use that parameter. We don't check flexor strength for flexible resins, but we need to see if it's a parameter that we need for application. Another thing here is viscosity. Just like I said before, high viscosity, it's not a good thing except if it's needed. So if I can avoid it's interesting because of the waste of resin. Teflon reactivity. So when I'm printing, when the curing process is occurring on the machine, the resin used to react with the Teflon. So when I have a high reactivity between the Teflon and the resin, it's not interesting for me because I will have to exchange this film fat more frequently than if I was using other kind of material or other resin. Stability of use, and it means I need to buy my resin today. I start using it today, and 1 month, 2 months, 3 months, a year after I start using, I'm having the same printing parameters here. So I if I'm correctly calibrating my resin, it needs to keep that stability between the time during the time. And the last one is batch repeatability, which means that if I buy the first batch of resin and then I change it when I buy the second one, my resin needs to have the same features. If it doesn't happen, it means that my manufacturer are not having a rigid quality control for the printing manufacturing. And The last thing I want to share with you is a little tip about softwares, free softwares for 3D printing. Here we have the left side software used to prepare the models to fix some missing triangles or some other kind of problems that used to happen when we scan the models. So is this software is the Mesh Mixer, which is developed by Autodesk, but it's free for use, and it really helps a lot when you are using to 3D printing. And the other one is Cheatbox, which is another free software that we can use for a huge amount of different machines here. We can configure directly from this software and use it to using directly for different kinds of machines. And we also can use it to make supports, to create structures, to holes, and a lot of other things that help on the process. And that's it for now. Thank you.
Okay, okay. Thank you, Mr. Bruno, for your explain. So, now let's do our raffle. Okay. Two words. Okay, please send us here in the chat. Okay. 1, 2, 3. Let's go, guys. Please. We have our winner. Now, Splinty Printer. Okay, Mr. 1 second. Mr. Hassan, this is our winner. Yes, yes. Congratulations, Mr. Hassan. Please, send us your contact here in chat, okay? Email address and phone number, WhatsApp, okay? Congratulations. Okay, thank you, guys. Thank you, everyone. And see you next webinar. Okay?
Thank you,
Thank
guys.
you, Bruno.
Thank you.
Bye bye. Bye bye.